Everyone, welcome back. Today, we're going to learn about the five kinematics equations. So remember last class, we talked about acceleration and how to read velocity versus time graphs and how to get acceleration from that. The first thing I'm going to start with is derive all these equations because it's important to know where everything comes from. So the first equation you just have to know is average velocity is equal to displacement over the change in time. So our first equation. That one we've talked about it earlier, you just know that one. The second equation, which is acceleration in terms of the starting and final velocity and the change in time, what we can do is first draw a graph of velocity versus time. This is the velocity over this period of time. And we're going to say at t1, the velocity is u, and then at t2, which is some later point in time, the velocity is going to be v. So in this case, u is going to be our starting velocity, and then v is the ending velocity. And from what we learned last class, acceleration is the slope of the velocity versus time graph. So how do you find slope from a graph? Well, you do y2 minus y1 over x2 minus x1, right? So this is the same thing. Just go like this. Acceleration, or the slope, is going to be equal to v minus u, because those are the dependent variables, or y, mine over t2 minus t1. That's basically the same thing as v minus u over delta t. So we're just calling the change in time delta t. Instead of two variables, we're just going to put it as one, because most of the times when you do a problem like this, they'll just give you the change in time instead of the starting time and ending time. This means that our second equation is A equal to v minus u over delta t. We have two equations down and three more to go. To find the third equation, which relates distance with velocity and time, we first also need to draw a graph of the velocity versus time. We're going to say velocity is like this, and then we're going to have the same thing again, the whole t1 and then t2, and then we're going to say the velocity here is u and the velocity there is v. How do we find distance from a graph like this? It's going to be the area under the graph. This entire area, t1 to t2, this kind of trapezoid, is going to be the distance traveled during t1 to t2. You can find the area of this graph because this is a rectangle and then this is a triangle, or you could have just done it this is a giant trapezoid and find the area there, but I'm just going to split it up into two different areas. So I'm calling this one D1, the distance 1, and this one's D2, distance 2. Distance 2, you can think of it as this area is equal to half base times height, right? Because it's a triangle. So the base is going to be T1 to T2, which is T2 minus T1. Like what we said earlier, T2 minus T1 is just delta T. So we're going to call it delta T. The base is delta T. Half base, which is delta T, times height. So the height is here to here, and that's V minus U. Half delta T times v minus u is the area for this triangle, which is also the second distance. At the end, we're going to add d1 and d2 to get the full distance. So yeah, this is just me splitting it up first. So now let's find d1. d1 is a rectangle. The area of a rectangle, as you probably know, is the base times the height. So again, the base is here to here, T1 to T2, which we already call delta T, and times the height, which is here to here. So this is just U, because this over here is 0, so the height is U. So that's the area for the rectangle. or d1. And to find the total distance, we need to add d1 plus d2. You'll get ut. So I'm just going to write delta t as t because it's more simple to look at. When I write t, it's really delta t. The overall equation is going to be ut plus half times v minus u times delta times t. Okay, we can simplify this into ut plus half and then vt minus half ut. From this, we're going to get e equals half of ut because ut minus half ut is just half ut plus half vt. In the end, that's equal to, you can factor out the half and the t. You just get half u plus v times t. That's the distance that you can calculate when you're given the starting velocity, the final velocity, and the change in time. So that's our third equation. So now moving on to the fourth equation, we're just going to use some algebra based on the previous equations to solve for this one. This equation right here equals v minus u over t can be rewritten at equals v minus u. That can be rewritten as v equals u plus at because you just add the u to both sides, and over here you multiply t to both sides. That is how people usually write the equation. It doesn't really matter because it means the same thing. I'm just rewriting the equation right there. We can change it into forms that looks like this one. Can have a d in the equation too, so we can find distance in terms of acceleration and velocity, because like the whole goal of these 5 equations is to describe all types of motion. We can find like any variable depending on what we're given. Over here, this equation 3 up here, the first thing we're going to do is add u to both sides. U plus v equals 2u plus at. To make this look like that, we need to multiply both sides by half times t. On this side, we're going to get half u plus v times t equals to half times 2u plus at. This side simplifies into u. This side simplifies to ut plus half at squared. This side actually can also be simplified. If you look at this equation that we derived earlier, half u plus times u plus v times t is equal to d, which is distance. So this is actually the same thing as distance. This becomes just d. That's our final like fourth equation. From this equation, you can find distance given the starting velocity and the acceleration. Now we're going to move on to our fifth one, where we're also going to use some algebra. First, we're going to start off with these 2 equations. A equals to v minus u over t, which is the second equation we derived. This one, it's the same thing. We're going to use d equals half u plus vt, which is the one right over here. The first thing we want to do is multiply both of these to get rid of the t, this t and that t, because if you look at all the equations that we just derived, they all have a t. So you want something, an equation that can help you figure out a variable without having to be given time. How do you get rid of the t? You have to multiply a times d, so a times d, and that would equal to v minus u over t times half u plus v times t, right? So this t and t cancels. What you have left is half u plus v times v minus u on this side, and this is just a times d. You can just use FOIL, like just multiply this, that. We'll get half v squared minus u squared goes to AD on this side. This is technically the last equation that we have for the 5 kinematics equations. But usually how people write it is that they bring this 2 to the other side. It becomes 2AD equals v squared minus u squared. Also bring the u squared to the other side. So you get squared equals u squared plus 2AD. This is the equation, doesn't have time in it. So you don't need to be given time to solve for v or u or a or d in this equation. That was the derivation of all these equations right here, basically. Kinematics is the study of motion or how things move. These equations, the ones that we just derived, are meant to be used for anything that has constant acceleration. By constant acceleration, it just means that acceleration can't change, can't equal to 0 when you're using these equations. And acceleration can be negative when you're using these equations. It just has to stay constant. The time it takes for a race car to cross the finish line is unknown. Race car accelerates from rest at 26 meters per second squared for a quarter mile, so 0.25 of a mile. What is the final velocity of the race car? First of all, your acceleration is given in meters per second squared. You'll have to convert the mile to meters. U, or the starting velocity, is equal to 0 meters per second because it's not moving. If it says the car accelerates from rest, it means that thing is not moving. Accelerates with an acceleration equal to 26 meters per second squared. They want you to find what the final velocity is. So what is v equal to? Distance here to here, total distance traveled during this period of acceleration is 0.25 miles. Right now we're going to convert this to meters because we have acceleration in meters. What we can do is have to know in 1 mile there are about 1609.34 meters, so 1609.34 meters in a mile. It's for 1 mile, but we have a quarter mile. Basically, you're multiplying this side by 1/4 because it's a quarter mile. The same thing as multiplying 0.25. If you multiply one side by 0.25, then you also have to do the same thing to the other side. What you're going to get is 0.25 miles on this side is equal to 1609.34 times 0.25. Use your calculator, you're going to get 402.336 meters. We're going to plug that in for the displacement. That equals 0. The displacement equals 402.336 meters. If you remember from the equation we derived earlier, you can see which one of these equations can we use. See that we have displacement, we have the starting velocity u, and we have acceleration, and we're trying to find the ending velocity, which is v. So if you look here, you can see which equation you can use. It's going to be this one because it has v, u, and a and d. Over here, you can write that down. V squared equals u squared plus 2ad. You can just plug everything in. V squared equals to starting velocity is 0 squared plus 2 times the acceleration, which is 26 meters per second squared, times distance, which is what we just found, 402.336 meters. That's for final velocity squared. So if we want just the velocity, we need to take the square root of the whole thing. So that's 2 times 26 times 402.336, and you want to take the square root of that entire thing. We're going to get 144.64, which is rounded to 145 meters per second. That's the final velocity of the race car. Have a practice problem. An Olympic sprinter starts a race with an acceleration of 4.5 meters per second squared. Assuming she can maintain that acceleration, what is her speed 2.4 seconds later? First thing you can do is write down what you're given. Acceleration equals to 4.50 meters per second squared. Time, the change in time, delta t, is equal to 2.40 seconds. Question says the sprinter starts the race with this acceleration, so that means that she started from rest. Because you start a race from rest, u equals to 0 meters per second. The question is asking what is her speed 2.4 seconds later. So speed is just the magnitude of velocity, which is velocity without the positive or negative sign, or just velocity without a direction, basically. You can look at what you're given. So basically what you want to find is velocity. You can find speed from there because speed is the magnitude of velocity. If you go and see the equations we derived earlier, we have the acceleration, the starting velocity, and we have the change in time. I'm going to rewrite this into the same thing, the same way we wrote it here. So v equals u plus at. Final velocity, which is v, equals starting velocity plus acceleration times the time. Over here, we know u equals 0 plus a, which is 4.5, times t, which is 2.4. You're going to get 10.8 meters per second. And remember, this arrow thing that I'm drawing is just basically showing that velocity is a vector. But sometimes I don't draw it because people will already know that it's a vector, so they don't need to write it. From here, we know that speed is equal to the magnitude of velocity, and since the velocity is already positive, and there's no direction other than a positive or negative sign, we know that the speed is 10.8 meters per second after 2.4 seconds. If you look here, our answer is B. That was just an acceleration of a person running. When you're on Earth, we actually are experiencing acceleration right now, and we'll learn later on why this makes sense. But basically what you need to know now is that acceleration causes a force. In our case, we are not floating away from Earth because we're experiencing acceleration due to gravity. So the force of gravity is keeping us on the ground. Technically, if you dropped a piece of paper, a ball, they will fall at the same height, at the same time. They will fall to the ground and hit the ground at the same time, be falling at the same rate. It's because they both experience acceleration due to gravity. That's the only force they experience that's created by the Earth. Except on Earth, we have air resistance, so that's the reason why they aren't falling at the same time and hitting the ground at the same time. Based on what I just said, theoretically, this means there's no air, anything will fall to the ground at the same time. This experiment was actually conducted by Neil Armstrong and the people who were on Apollo 11 who went to the moon. They dropped a feather and a hammer, and they both fell to the ground at the same time because they were both experiencing the acceleration due to the moon, and there's no air basically on the moon, so there's no air resistance, so they both hit the ground at the same time. In a vacuum, basically some enclosed space where all of the air is taken out of there. So there is going to be no air resistance, basically. There's a video of Brian Cox, who's a very famous scientist over in the UK, and he's going to do an experiment, feather and a bowling ball, and we're going to see if they fall at the same time.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems. And that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCB 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Look at that.
They came down exactly the same. Wow.
Look.
Watch right there. Look at how they hit right there.
Exactly.
You're back on the side.
Exactly the same.
Feathers don't move, nothing. Look at that.
That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's a force pulling them down, gravity. But Einstein imagined the scene very differently. The happiest thought of his life was this: the reason the bowling ball and the feather fall together is because they're not falling. They're standing still. There is no force acting on them at all. He reasoned that if you couldn't see the background, there'd be no way of knowing that the ball and the feathers were being accelerated towards the Earth. So he concluded they weren't.
That video was very interesting, right? Because you could see the bowling ball feathers falling at the same time when there was no air around, basically. You can kind of try the same thing at home if you grab like something like a tennis ball and then you grab a book, but you put the paper on top of the book and then you let both of them fall. The book will kind of take away some of that air resistance and the paper will just fall like on top of the book with the tennis ball. So what is acceleration due to gravity? Basically, all objects near the Earth's surface fall with an acceleration of about 9.81 meters per second squared, which is sometimes rounded to 10 meters per second squared. We're probably going to keep it at 9.1 meters per second squared. And this is the rate of acceleration they fall at when there's no air resistance. Acceleration due to gravity has its own special variable because it's used so much to calculate stuff in physics. It's just labeled g. Gravity is the force that causes objects to accelerate downward towards the center of the Earth. That's what's keeping us on the Earth, and that's what's keeping us from flying into space. And then how you calculate the force of gravity is Fg. So the force of gravity is equals to m times g, where m is the mass and g is what we just said, acceleration due to gravity. So g is technically for the Earth. Value of 9.81 meters per second squared is for the Earth. So once you go to different planets, the acceleration that keeps you on the planet is going to be different, because this value, what it depends on is the mass of the planet itself. So the heavier the mass of the planet, the more force you're going to feel pulling you onto the planet. This is actually for like any celestial body. It can be like a star or a moon. So for example, the gravity on the moon is 1/6 of the gravity of the Earth. In kinematics equations, so basically the 5 equations we just did, we have something that's falling and we're going to calculate its acceleration, like velocity or the distance it falls from its acceleration. Sometimes we're going to use negative g, because it depends on which way you're going. Sometimes when something's like flying up, we're going to say g is negative because the acceleration is going down, but we're going up, so opposite directions. So we'll have a negative. A common way to describe acceleration is to express it in multiples of g, just the acceleration in terms of as a factor of g. Some things we use to describe the acceleration in terms of g are roller coasters. So there are certain roller coasters very dangerous to ride because the g, like it has so many g's, can have like harmful effects on your body. Besides roller coasters that we express in g's are like jets. Like sometimes we say like, oh, this jet is going at like this many g's. The pilot of the jet will experience this many g's when it's going this fast. First we're going to do this example and we're going to take a look at this roller coaster, and the answer we get here is the amount of g's you would feel while riding this roller coaster. So it's a pretty intense roller coaster actually. If a roller coaster accelerates at a rate of 39.2 meters per second squared, how many g's do the riders experience? Example is just really easy. What you need to do is divide a by g to see how many g's this acceleration is. How many times this g goes into this acceleration. So the acceleration is 39.2 meters per second squared. This is a good number to memorize, by the way. G is equal to 9.81 meters per second squared. From that, we get 3.99996 meters per second squared, and that rounds to about 4.0. This is how many times this goes into the acceleration. So these units actually cancel already. So this is how many times. This is about 4. If you rode this roller coaster, you would experience about 4 g's. What you're experiencing right now is 1 g. You're just standing because that's the force of gravity holding you down. Now imagine 4 times. Now we're going to see what it's like to ride a roller coaster like that. Okay, if you thought that looked scary, actually quite scary because this is considered on the more intense side of roller coasters. 4Gs is kind of but that's a real roller coaster, so it does exist. You can ride it somewhere, but there's like a certain amount of Gs you can go up to before like it's a fatal ride because your body can only take so much force. A person standing on the edge of a high cliff throws a rock straight up with an initial velocity u of 13 meters per second. So A is calculate the position and velocity of the rock at 1 and 3 seconds after it is thrown. Ignore the effects of air resistance. For all the problems we do, we're going to ignore the effects of air resistance because calculating the force of air resistance is another equation, and that's probably a little bit more complicated. We're just gonna do it without air resistance. B says find the maximum height that the rock reaches. So let's start with A. We can draw a picture first. So let's say we have this rock. Person is throwing it from here, like at the edge of a cliff. This will, I'm just going to draw as a rock. You can ignore the person. So it's starting here on the edge of the cliff, basically, and it goes straight up with u equals 13 meters per second. After it reaches the top, we know it's going to fall back down because there's gravity acting on it. So basically there's an acceleration acting in the opposite direction, the velocity. So this rock will eventually have to change direction. One thing we know though is that at the very top, when the rock is thrown, it'll go up and it'll stop for a little bit, like just a split second, stop and then fall back down. At the highest point, the velocity is going to equal 0 meters per second. So we're going to need that in B. But let's start with A first. We have this starting velocity and we have the acceleration, which is negative g, or negative 9.81 meters per second squared. And it's negative because it's acting in the opposite direction, right? Because the rock is going this way, but acceleration is going down. We have those two values, and then we also are given time, and they want the position and velocity. I want to find V, and we want to find basically D. And we're also given T, I'm going to call this T1 is equal to 1 second, and then T2 is equal to 3 seconds. So over here, we can decide which equation should we use. To find the distance, we're going to use this equation because it has everything that we're given. We can use all of that to find D, which is what we're looking for. For T1, so basically after 1 second, we're going to say D1, which is the distance that it travels in 1 second, is going to equal to the starting velocity, which is 13 meters per second squared, times T1, which is 1, plus half, and then the acceleration is negative g, for negative 9.81, and then times t squared, which is 1 again. And then if you plug all of that into your calculator, you're going to get 8.10 meters. So after 1 second, this rock travels 8.1 meters. Now let's find the velocity for the same amount of time. For this, the equation we're going to use is v equals u plus at. Basically, how I decided on this equation is that I looked at what I was looking for, v, what I have, which is the starting velocity u, acceleration a, and the time t. For this, v is equal to 13 plus, again, a is negative g, or negative 9.81, multiplied by T1, which is just 1 second. If you plug that into your calculator, you're going to get 3.19 meters per second. This is positive 3.19 meters per second because remember, velocity has a direction. Basically, since it's positive, we know the direction will be up because we're calling this the positive direction and we're calling this the negative direction. So that was for the T1, and now we're going to repeat the same thing for T2. The distance that the rock will travel after 3 seconds is going to be 13 times the time, which is 3 seconds, times the time, which is 3 seconds, and then plus half times negative 9.81 times the time t, which is 3 squared, going to get 6.38 meters. At this point, the rock is probably somewhere up here. If the distance was negative, that means that it will be below the rock's starting point. So basically over here, the distance equals 0 meters. So like after 3 seconds, the rock is somewhere up here. But if the distance becomes negative, the rock is going to be down here. So this is V1. V2 is also equal to U plus AT. We can use the same equation because we're given the same things and we're looking for the same thing. That is going to be 13, same starting velocity times negative 9.81. And the only thing that changes is T, which is 3 seconds instead of 1 this time. We are going to get negative 6.62 meters per second. So what does this mean that the velocity is negative? It's that this rock, instead of moving up, it's moving down, but it's still above its starting point. So it's probably somewhere, so the rock has gone like this, and then now it's like somewhere here because it's moving down, but still above the starting point. And now the last thing we're going to do for today is find the maximum height the rock reaches. Basically, how you find the maximum height, we're going to call it H max is equal to, we need to find H max, which is basically the same thing as distance the rock travels at the farthest point. The equation we can use is V squared equals U squared plus 2AD, where this is going to be H max. So if we solve the equation for H max, we're going to get V squared minus U squared over 2A. And we just plug everything in from this point. V we know is going to be 0 because it's at the highest point and the rock is going to stop at its highest point. So it's going to be 0 squared minus starting velocity, which is still the same, 13 squared over 2 times acceleration due to gravity, which is negative 9.81 because the acceleration is downwards. And we're going to get an answer of 8.61 meters. So that is the maximum height that the rock reaches. That's it for today. So we're just stopping here at gravity. Next week, we're going to do some gravity practice and then move on to Newton's laws and forces. So yeah, thank you.